It's a pleasure to be presenting here to begin on basic semantics. And okay, my presentation will be on many different subjects, and I'll try to present as many results as I can. But so let's see how far we can get. So first things first, proof-theoretic semantics, for those who don't know, is an approach in which we try to substitute traditional notions of logic, such as truth, which are very tied to modern theory, by notions which are more aligned with the proof-theoretic tradition, such as the concept of proof. And we try to do semantics with it. In fact, we consider proof as one of the basic concepts of semantical analysis. And PTS now is a very broad approach, but I will in this talk consider specifically one branch called basic sense semantics, which is one of the most fruitful branches nowadays. And I will try to show things we can do with basic sense semantics. So different logics and different contexts in which we can use basic sense semantics in many different contexts to show how powerful and flexible it is as a semantic framework. Okay, so I will present at least two frameworks in a reasonable amount of detail, logical ecumenism and logical bilateralism. If there is enough time, I will briefly mention three other results and three other contexts in which we have very nice results with very specific properties, very distinct properties. But as I mentioned, only if we have enough time, so I will prioritize the ecumenism paper and the bilateralism papers. And the ecumenism paper was just accepted for publication, so it is the only slightly older result. But okay, so let's get started also, because let's see how much we can do. First of all, I will present an introduction to basic sense semantics, because I don't want to assume any sort of specific background. Okay, so the main idea and the mathematical definitions will be on the next slide. So this is just for an overall idea of what's happening. We start by defining a set of inferences. So you can think of those as, for instance, a set of beliefs about what we believe we can infer about specific facts. For instance, I can say, I am now in Tübingen, therefore I am now in Germany. And this is an inference that we would consider valid, but it's about specific facts, it's not a logical inference. And I take a collection of inferences and use it to define the concept of base. Then using the concept of base, since it is basically a proof structure, I can define a notion of proof for that base. And I say that something is provable in a base if I can derive that information from the empty set of assumptions. And then I have an atomic notion of proof. After I have defined an atomic notion of proof, I also extend it to non-atomic formulas, which I do through semantic clauses. So for instance, we consider that we have a proof of A and B, if and only if we have a proof of A and a proof of B. I might actually use the stick, if it would be good to make possible. So we have a proof of A and B, if and only if we have both a proof of A and a proof of B, which is an intuitive concept of the proof of conjunction. And after we have defined the notion of proof for atoms in a base, and the notion of proof for non-atomic formulas in that base, we can define logical validity as validity regardless of the base. So regardless of what particular set of inference I consider, what is valid in all such bases is valid logically, which is a quite sensible approach. So now for the formal definitions, we define the notion of atomic rule. This is just an introduction rule in which we use atoms. And it's important to mention that these rules are not closed under substitution. They are material inferences. They are particular facts. So for instance, the rule that lets you conclude Q from P, you can only use the atom P specifically and the atom Q specifically. You cannot use any other atom. And of course, we also allow rules that discharge assumptions. We can also allow rules that discharge other rules. In some contexts, it makes a difference. In others, we can prove equivalence results. There is one context I will mention in which this makes a difference, but I don't think I will be able to get into that much detail. But it's nice to know that we have this. And okay, as I mentioned, our base is just a set of any set, including the empty set of material inferences. We have a notion of deducibility for such bases, which is just a consequence between a set of atoms and an atom holds in a base. If you are able to produce a deduction with P as the conclusion and the set of atoms gamma as premises. And after you have defined basis, deducibility for basis, you also define a notion of extension, which is set theoretical. So you say that a base extends another if and only if you obtain the extension by adding a possibly empty set of rules to the original base. This is an example of a deduction, of an atomic deduction, but I won't spend too much time on this because I have to assume a familiarity with method deduction in this talk. So, but this is just an simplification of how things work. And as I mentioned, after we define a notion of proof for atoms, we extend the notion to non-atomic formulas. And this is done in a specific way. It follows an old idea by Gentzen, in which we read the introduction rules of method deduction as definitions of the connective. So for instance, since in order to introduce A and B, I have to prove A and I have to prove B, this is taken as the semantic clause in the basic extension approach to the semantic, it's taken as the definition of the proof of A and B. And there's a very well quoted excerpt by Gentzen on that matter, but since time is restricted, I won't. But the slides are going to be available afterwards, and there's a lot of information on those photos who want them. And okay, this was the basic idea, but it doesn't work exactly as expected, because there is a paper by Thomas and Peter and Wagner's sons saying that if we define a disjunction as holding if and only if, so I have a proof of disjunction if and only if I have a proof of one of the disjuncts, we do not get intuitionistic logic, we get incompleteness results from that clause. And Thorson has proved that if we use instead this semantic clause, which is basically the elimination rule for disjunction. So a disjunction holds in a base if in all of its extensions, if I can get an atom from A and I can get an atom from B, then I already have that atom. This is basically the elimination rule for disjunction, but restricted to atoms. And if we define disjunction like that, we get completeness for intuitionistic logic. And also, you can also say that in the case of absurdity, it's not necessarily what you would expect, because although Dummett argues that this should be the introduction rule or some version of it to bottom, it could be argued that instead bottom is a formula which has no introduction. So this would be the clause you expect to use, which says that you never have a proof of bottom. But that case also does not work, because if you use that, you can show that the double negation of every atom holds. So you cannot use this clause and you cannot use this clause. And if you define bottom in terms of explosion, so you have a proof of bottom, if you can prove every possible atom, then you get completeness for intuitionistic logic. And these are the semantic clauses. So I haven't maybe mentioned everything intuitively until now. So again, an atom is supported, it's valid if we can prove that atom in the base, and conjunction is just have to prove both conjuncts. And I just mentioned the bottom and disjunction clause. In the case of implication, we already also have an additional structure, because we don't want implications to hold vacuously. We don't want to say A implies B holds just because we cannot show, we don't have a proof of A. So we define it more strongly by combining these clauses, by saying that I have an implication if in every extension in which I am capable of validating the antecedent, I can also validate the consequent. So we actually turn our attention to the basis where we actually have the constitutive antecedent and consider if we can prove the consequent or not to evaluate these functions, which is if you think of this, for instance, in terms of colloquium model, is the modal reading of the implication, for instance. And of course, we define logical validity by quantifying over basis after everything is done. So this was a brief introduction to basic and semantics to what we already have. And I am going to start by showing what we can do in the context of logical ecumenism with this. So very briefly and very broadly, in logical ecumenism, we want to provide an environment, like a logic in which distinct other logics can coexist. In this case, we are doing specifically with classical and intuitionistic logic. And we are doing ecumenical PTS, and we are doing specifically a semantic framework in which we have different notions of proof. And they coexist, and they yield semantics for an ecumenical logic. So I will explain what I mean by that in just a minute. And of course, there are different ways of defining what a classical proof is. Intuitionistic proof is just the notion that I just mentioned, that we have the ability of formulas and then we extend them to proof clauses. But now we define a classical proof as a proof of consistency. So if I can prove that a formula is consistent, then there is a classical proof of it, which is a weaker notion, and we can read it into Hilbert. I also have this very nice quote here explaining the idea. So if something is consistent, then in a certain way it is true, so you can say that you have a classical proof of it, or at least you can provide a classical proof of it. So we are going to formalize these two notions to provide an ecumenical semantics, but before that, since I use the notion of consistency here, and as I mentioned, bottom in basic sense semantics is defined through logical explosion and not consistency, I have to make some remarks first on treatments of consistency we can provide in basic sense semantics. So there are more than one possible way of defining bottom. The traditional way is to Torson's clause, in which bottom is not an ultimate formula, it's just a logical constant. And we define validity for it in terms of explosion. It is also possible to treat bottom as an atom. So since it's an atom, and we have bases capable of manipulating atoms, it can appear in the rules of the base. And we do that, but we also require that in every base there are rules that allow us to prove any possible atom for bottom. If we do that, the two approaches are more or less equivalent. You can prove that you have more or less the same semantics for bottom. What you cannot do, as I also just mentioned, is define bottom in terms of a semantic clause. So bottom is not an atom, and you say that bottom is never valid. Because you can prove, if you do that, that the double negation of every atom holds in every possible base. And there is also a quote by Thomas Peter explaining why this is the case, because basically you can always create an extension validating exactly what you want. You don't have any restriction on what extension you can obtain. And this generates, in this case, this sort of undesirable behavior, let's say. Okay. You cannot define bottom in terms of semantic clause that is never satisfied. But surprisingly, you can define bottom as an atom and stipulate that it is never derivable. So you define bottom as an atom that can appear in base, but you say no base is capable of validating, of deriving bottom or producing a proof of bottom. If you do that, we have shown in the paper that you can have a constructive. Sorry, in the completeness proof. You can prove soundness and completeness for intuitionist logic constructively if you only take consistent bases and consistent extensions of bases. And more importantly, in this talk, some of the results we are going to prove for ecumenical logics, they use the consistency requirement essentially. And we are also working on some additional ideas on ecumenical PTS, which are not on the paper, but we are currently developing them, which also depends essentially on the consistency constraints. So it seems that the properties you get out of the semantics change significantly if you use this definition. So I won't have time to get into much detail how the proof works, but I will comment on some features of it at the end of the talk. But okay, for now, it's just important to know that we can define bottom as as an atom and require it to not be derivable. And that is the case because what is different between this definition and this definition? The difference is that if we, for instance, consider a base which is this rule, since we now we stipulate that we can never derive this. So if a base contains this rule, it will never, no extension of it will be capable of producing that on P, because any such extension will be inconsistent, and we exclude inconsistent bases from by definition. So we are essentially allowing a base to restrict their possible extensions by the shape of the rules they contain. And this is for a richer structure, and then we can avoid the results, the undesirable results that Thomas and Peter and Wagner showed for, which you can prove double negation for everything. Again, there's a lot of information in the slides, but I will not stay on them for a long time just to be able to present as much as possible. But that is why it works if bottom is an atom, but it doesn't if it is a logical constant. Okay, after we have defined bases this way, the semantics this way, but we require bases to be consistent, we can define an intuitionistic notion of proof for atoms, which is just the same as before. An atom is intuitionistically provable if it is derivable. But we can also now define a classical version. In the paper, we also consider a version in which, so first, we define an atom as being classically provable if in every possible extension it is consistent. We also consider in the paper a notion in which we don't have this quantification of extensions. We just have that an atom is classically provable if and only if it is consistent, but I won't have time to show every result in that paper. So for now, let's just focus on this semantic specifically. And okay, in the ecumenical semantics, we just, for the intuitionistic formulas, you can see now that most formulas have superscripts. Intuitionistic formulas is the same as before, but now we have the notion of proof for classical proof for atoms, which I just mentioned, and also a clause for extending proofs to non-atomic formulas, which are also in terms of consistency. So you have a proof of something constructively. If you can provide a proof of that something, and you have a proof of something which is classical, if you can show that it's consistent and it works for atoms and for formulas in general. If you do that, you can show that the resulting semantics is sound and complete with respect to the calculus obtained by adding these two rules to intuitionistic natural deduction. And of course, this is just the classical reduction and this is an elimination rule that is based on this introduction rule. So this is what we would expect of a reasonable notion of classical proof. So of course, that's also something that you similar to what you expect in an ecumenical approach, since we want to this distinct notion of proof. And we can actually show soundness and completeness for it. And as I mentioned, I won't have time to go into full detail on how the proofs work and what is different in this approach and the previous one. But I will mention for the technical audience on some of the differences in this proof. The first one is that when we are proving completeness, we do need to use classical reasoning, but only in the proof of classical inductive steps. So you can say that the proof itself is ecumenical, because if you keep yourself to the intuitionistic fragment, the proof is entirely constructive, but when you look at the classical fragment, you actually need to use classical reasoning. So that's, of course, in the spirit of ecumenism. Also, as I mentioned, we now require this to be consistent, and this creates an additional difficulty because in the completeness result, we require the creation of a base, but now we have to show that it's consistent. And we do that by proof because it's a base created to simulate the structure of a logical calculus. We can apply normalization strategy to it, and it is used the consistency of the base. And this is interesting because we are dealing with a notion of semantics which is based on proofs. So when we actually require some kind of essentially proof-theoretic reasoning, like a normalization proof, to show a semantic result, like completeness, I think it goes in the direction of showing that is in fact a novel and different semantic approach. And the final thing I would like to mention is that we have a completeness proof which still uses some strategy, but now it is slightly different. So now we divide it in two cases, one in which there is a consistent extension of the base validating the gamma, and in that case we are able to generate a proof of A from gamma. And if there is no such extension, we can actually produce a proof of bottom from gamma. And in this, for some time, I wonder myself if this was a constructive proof or not. And I asked Luis Carlos this in a very recent meeting we had, and he asked me a fundamental question. Also, are the extensions you are using decidable? And I said yes. And then, oh, then the proof is constructive. So because we are using the fact that either the base is consistent or it's not, but we only use that information for decidable extension of the base. So the proof of completeness in this case is constructive. Okay, that is what I wanted to present for the first result. I am going to present in more detail. The second one is on a different context called logical bilateralism. So the idea behind bilateralism is that now we don't reduce negation to affirmation of stuff. We say that assertion and rejection are two independent, conceptually independent speech acts. So I cannot say, for instance, that rejecting something is the same as proving that something is contradictory, for instance. And the bilateral systems that we define, they incorporate somehow this idea, which we have different rules for proof of connectives and different rules for refutation of connectives. And we do expect some kind of interaction between them, but we don't expect full interreducibility of one to the other, because, of course, the idea is for them to be kept separate. And what I'm going to present is a basis and semantics for it, but I think the most interesting part of this result is that we actually get to prove some new results, specifically in the bilateral framework, which are quite interesting. Okay, we are using specifically Bunsen's bilateral bi-intuitionist logic to ink. Sorry, let me just. We are using specifically this bilateral logic by Bunsen. We are also using a variant of his system, which is deductive equivalent, but it's still not the original system. And there is a reason for this, because if we try to read semantics directly from the rules, if you look at Bunsen's system, it does not work. We have actually counterexamples to it working. But if we instead pick a system which is equivalent, which only has some minor changes, then we can read directly from the semantic clause. And this already gives us a nice insight, which is we can't always extract the proof conditions of a system in Bayesian semantics by just looking at the calculus. Sometimes we have to consider additional things, and it will be clear why that is the case in a minute, because I will explain what changes. So just a very quick exposition of Bunsen's system. The rules for implication and conjunction. And as I said, we have both rules for proofs and rules for refutations. So the proof rules for implication and conjunction remain the same. There is some extra structure here, but I will explain in a while. The introduction rules for disjunction stay the same. And you can see also that I have some rules with a single line and some rules with a double line. A single line means that I have a proof of A, which is either is an assumption or there's a deduction of A which ends with a single line. And if I have a double line, then this is also either a negative assumption or I have a proof of B that ends with a double line, or that is with a refutation rule. So double lines represent refutation rules, single lines represent proof rules. I also have positive and negative assumptions, which are, I assume that you can read it as saying that this is assuming that something has a proof, and this is assuming that something has a refutation. When I have a dotted line, I am saying that I can either use the single rule, the single line, or the double line, but I have to, if I use the single line here, I have to use it here and here as well. I use double line here, and here as well. And they say that if I have A or B, and from A I can get a proof of C, and from B I get a proof of C, I get a proof of C. And likewise, if I get from A or B, I can get from A I get a refutation of C, and from B I get a refutation of C, then I can get a refutation of C. And also in the bottom we have this dotted line that from a proof of bottom I can get either a proof of A for any A, or a refutation of A for any A. And everything else is exactly the same, but we also have co-implication, which is something like I can prove a co-implication if I have proof of A and a refutation of B. Let's not get into too much detail, but those are the connectives. And the only difference between this system and the Bunsen system, because in Bunsen system, this will only be a single line. here and single line here as well. And we can show using this system that you can derive, that this rule is derivable. But okay. And in the refutation side, it's very similar. The co-implication now becomes a sort of implication, but reversed. And it's important to note that now I am dealing with refutation. So I say, for instance, that in order to refute A or B, I have to have both a refutation of A and a refutation of B. So you can, we are dealing with refutation. So I will go into more detail on that in a minute, but it's important to note that we are still doing an intuitive reading of what a refutation is. But okay, I will comment more on that in a minute. But the rules are quite symmetric to the proof rules. Okay, there is let's say, straightforward way of obtaining basic semantics for this. Since before we had the notion of proof, and it gave intuitionistic semantics. And now we have proofs and refutations in general, a calculus with proofs and refutations. We can also think of atomic rules for proof and atomic rules for refutation. So we allow atoms to be assumed positively and negatively. We allow rules that consider if we have a proof of something or a refutation of something. We also have proof rules and refutation rules, which allow us to prove and refute atoms. So it's just the same idea of the calculus, but now taken to the bases themselves. And of course, if I do that, and I can define a notion of proof for atoms, which is just a deduction which ends with a single line, and a notion of refutation for atoms, which is just a deduction that ends with a double line. And of course, the semantic clauses are exactly what you expect. So I have a positive notion of support. So something has a proof in a base if you can prove it atomically. So I limit that single line. And as I mentioned, if you use Vansing's original system, you cannot read directly a semantics from the rules, because, and this is the explanation why. When you define bottom now, you have to quantify over both positive and negative atoms. And this is what I mentioned when I said that you have counterexamples of this. So if you try to define bottom, I think that I can have a proof of bottom if and only if I have a proof of every atom. It does not work. The semantics does not work. It's not a semantics for Vansing's logic. And we also have this in the case of disjunction. We have to consider proofs and refutations of every atom. Which is already a point of where this diverges from traditional basic extension, but it's not the result I would like to highlight the most here. And of course, you also have refutation clauses which have exactly the same thing. Okay, so until now, it was a straightforward, let's say, extension of the traditional basic extension results. So we pick basic extension semantics, you bilateralize it, and we get our semantics for bilateral logics. But there's also some additional features which rely heavily on the fact that we have atomic proofs and atomic refutations. So as I mentioned, we have a notion of proof and refutation that are supposed to be non-interreducible. I cannot use one to define another. But they are not completely independent, and they shouldn't be independent. Because, for instance, when we consider what is a proof of A and B, we say, oh, I have a proof of A and B. If I have a proof of A, then I have a proof of B. So if that is the definition of what is the proof of A, then from that already follows what I should expect in order to obtain a refutation of A and B. So if to prove A and B, I have to prove A, and I have to prove B, then if I can either refute A or refute B, then I should be able to produce a refutation of A and B, because this information is incompatible with this information, right? So you expect them to be different, but you should expect it to be some kind of isomorphism or relationship between proof conditions and refutation conditions. And this is in bilateral logic in general. And there's a paper by Nissim Francis which calls it horizontal universal principle, which is that you can read the proof conditions for a formula from its refutation conditions and vice versa. And the interesting, okay, so we have a notion of duality that allows us to prove that. So for instance, you can say that the proof conditions for A and B are isomorphic to the refutation conditions for A or B. because, as I mentioned, if you want to prove, if you have a proof of A and B, you have a proof of A and a proof of B. And if you have a refutation, you need to have either a refutation of A or a refutation of B. So I am saying that basically the notion of duality says that the proof and refutation conditions are isomorphic. It is a description of duality for formulas, which is used to study bilateral harmony. And the interesting thing about basic and semantics is that now we have some kind of difference between proofs and refutations already at atomic level. So since we have a notion of isomorphism for proofs and refutations, we can also think of a notion of isomorphism for proof rules and refutation rules. So I say that if I have a rule of this shape, then I will take its isomorphic dual by changing the polarity of every premise, changing the polarity of the rule itself. So if it was a proof rule, now it is a refutation rule. And if, for instance, if you require a refutation of Pn, now it requires a proof of Pn. Also, if it was capable of discharging a set of positive assumptions gamma, it now discharges negative assumptions gamma, and the opposite also holds. So I basically invert everything about the rule, and I get a notion of duality for atomic rules. Once I do that, I can also define a notion of duality for deductions, which is just you get the dual of the deduction by replacing every rule in it by its dual, and every assumption, every positive assumption P by a negative assumption P, and vice versa. So it's really the isomorphic deduction that will take by changing everything. And also a notion of dual base, which is just what a beta base you get by replacing every rule by its dual. And it's important to remark that duality in all cases is involutive, which is something we use in all the results. And the interesting thing is, once you define duality for rules, deductions, and bases, you can prove some very interesting results. Yes, okay, as I just mentioned, we just invert the assertoric part of the deduction to obtain the dual deduction. And of course, if we have a deduction, atomic deduction in a base B, and we take its dual deduction, then we can show that it is a deduction in the dual base B, in the base that is dual to B. And okay, just so to ease the notation, I define that the dual of the positive sign is the negative sign, and the dual of the negative sign is the positive sign. And the result, the basic result, the first result we have shown is that if we have a deduction in a base that shows a consequence positively, and you take the dual deduction, and it is a deduction showing the same result but with opposite polarity in the dual base. So once you pick a deduction and you flip it around, you get a deduction in the dual base. And if the original deduction was a proof, the dual deduction is a refutation. This is what's pictured here. And you prove it at first for bases, but it can be extended to formulas in general. So if you have a proof of A in a base B, you have a proof of A in a base B, if and only if you have a refutation of the dual of A in the dual of the base B. And if you have a refutation in A, it also works. And you can also define it for consequence in general, provided you define also a notion of duality for sets, which is just the set of the dual formulas. So the set of the dual of delta is just the set of all formulas which are dual to the dual of delta. And what is interesting about this is that it allows us to give a semantic reading, a proof-theoretic semantic reading of what is bilateral harmony in the first place, because you can say, now we have a duality notion for atoms. So we have atomic proofs, and we can dualize them to obtain atomic refutations. And you can say that, okay, bilateral harmony is just preservation of the dualities that you already have at the atomic level. So you have a duality notion for atomic bases, for atomic proofs, and you say that semantics preserves this duality, is harmonic if it preserves its duality by the semantic clause. It is just satisfaction of these two properties. So it allows a semantic reading of what bilateral harmony is, which is a quite interesting result and it is very proof-theoretic. There's also some practical uses because we can, for instance, use this proof embedding results because we are not reducing, but showing that one fragment is representable in another fragment if we just consider a different set of bases. And of course, this is only a result we can prove only because now we have additional structure in the basis. So since now we have proof-theoretic structures in basis, we have isomorphism between them, now we have also new kinds of semantic results we can prove using it, which is, I think, why it's interesting to stand this in the first place. We are also working on different bilateral results, which is just in inverse logic, you can have a proof of an atom, a proof of the same formula while you have a refutation of the same formula. I like to explain this by saying that 2int is logically explosive but epistemically persistent, because you do have logical explosion. So from a proof of bottom, you get a proof of A for any A. And for a refutation of top, you get a refutation of A for any A. But you do not have some, for instance, that if you assume a proof of A, refutation of A, you get anything. It does not hold. So if you have a proof of A and a refutation of A, you cannot necessarily get a contradiction from that. So this might be a good property in some contexts. For instance, if you are using bases as, for instance, they are the beliefs of an agent, and they are used to represent that. It's okay to let them be inconsistent, because an agent can have inconsistent beliefs. But if you are, for instance, reading a base as a set of mathematical inference, you're using it to model mathematical proofs, and you don't want something to be both provable and refutable. So this is not an ideal property in this particular context. So we are now working on a different logic which is obtained by adding these rules to balancing system. So from a proof of A, the refutation of A, I get a proof of bottom. And from a proof of A, the refutation of A, I get a refutation of top. And if we use the consistency constraint again to say that okay, no basis can prove bottom, no basis can refute top, and all bases have to prove top and refute bottom, then it is our belief, we are working on it, that just by adding these atomic rules to every base, we get the semantics for this logic. And we are also working on the proof theory of this logic because it seems to be very well behaved. It's a normalization, such that a lot of interesting properties. Then we also have, okay, first, this extension is also interesting because it seems to model quite well David Nelson's notion of constructive falsity, in which you have a notion of rejection that is stronger than a notion of negation. You say, I reject something by providing a counterexample of it. And if I have a counterexample, I can show that by assuming it, I can produce a contradiction. But I cannot, by assuming it and showing a contradiction, necessarily provide a specific counterexample of it. So there are two negations, one which is stronger than the other. And this logic seems to be a good fit for that notion. We can also prove additional semantic results. For instance, we can in fact prove, we have added these rules for atoms, atomic rules. And of course, if we have a proof of P and a refutation of P, we can produce bottom, which is forbidden. So by including these rules, we never can produce, we are saying that no extension of this base can be able to produce a proof of P and a refutation of P. And we can show that it extends to all formulas. So if I have a proof of A in a base, I cannot have a refutation of A in the same base. Likewise, if I have a refutation of A in that base, I cannot have a proof of A in that base. It does not hold in balancing semantics, but it does hold in this. And this is shown by using some results related to semantic harmony and the consistency constraint in an essential way. So it's actually required for the semantics to work this way. Okay, those are the main results I wanted to present. I do have, I think, some minutes that I could use to present the main results. So I won't try, it will be very briefly, but I will mention 3 other results that I will use base extension. Okay, intuitionistic linear logic is a logic in which you consider now, instead of general formulas, some notion of resource. And we can, in fact, obtain base extension semantics for intuitionistic linear logic by introducing some notion of resource which is incorporated in the definition of base extension semantics. There are at least two ways to do so. There's the formless resources approach, which I will explain in more detail in a minute, which was developed by David Ping, Alexander George, and Tal Brown and Buzoku. And there is one that we are developing as well, which is the inferences and resources approach. In both cases, we need to add additional structure to the atomic basis to be able to formulate this resource sensitivity notion. So we now use multi-sets of assumptions instead of sets. And we do not allow vacuous discharge anymore, which is very important for some properties I'm going to show later. And in both cases, Barroso has shown that we need that if we have also additive and exponential connectives. So if we have atomic rules which are sensitive to the context that they require for the application, we can also define semantics for the full linear logic and not just because it was initially developed only for the multiplicative fragment. So it has been shown now for the entirety of intuitionistic linear logic. So as I mentioned, I will be very brief. I will only explain the main idea. I will not even show the semantic clauses just because of lack of time. But the main difference is that now, as I mentioned, there are two approaches. In one of them, we now, instead of defining atomic supports by considering proofs from empty assumptions, we consider proofs given a set of atoms. So P holds in a base given a set of atoms if and only if P is derivable from that set of atoms in the base. And we define validity by considering what is provable in all bases with the empty set of resources. Intuitively, it means that we are using the rules are tools that are capable of producing atoms from other atoms. So we use atoms as resources to produce other atoms. We use that to define logical validity. But we can also have a notion of a different definition in which we take the inferences themselves, the rules of the base to be resources. So now we take it a base to be a multi-set of resources. Some you can use only once, and some you can use as many times as you want. And we are now back to define it in terms of proofs from the empty set. But now we use a set of inferences here to show that I did prove P, but I used the particular set of one-time use inferences in gamma. And the interesting thing about that is that now you are allowed to quantificate existentially over the set of resources. So you say that from gamma follows A in a base, if and only if there is some set of resources in that base which is capable of witnessing the implication. And of course, if there is not, if gamma is empty, you will say that A holds in that base, if and only if there is some set of resources in that base that's capable of producing that formula. And then we can quantify over the basis to obtain logical validity. Okay, both approaches that they have the strengths and the weaknesses, and which one we should use depends on the context. There are, in fact, some ideas that seem to work better in some approaches instead of the others. I know that Barroso is also working on an approach which is much better in this framework, but I'm not going to talk about it right now. You can see the second approach in which you have inferences as resources as a kind of generalization of the first approach. However, you bring in extra structure, which also brings in additional difficulties. So, for instance, you have trouble defining semantics for the top constants, unless you use higher order roots in the base, which are rules capable of discharging other roots. So you get extra power, but there is some cost to be paid. And as I mentioned, for some ideas, it's just less intuitive. One idea is more intuitive than the other, depending on what you are thinking about. But it's good to note that there are two different notions of resource which yield reasonable semantics. But also, if you want specifically a notion of base validity, what is to be valid on a base, then the second approach is also better because of the properties it has. And there's also an intermediate approach, which has some features of one and some of the other. Okay. The main point of this short presentation was to show that it can be done, that there's more than one way to do it. But that is all I would say about linear logic. Now I'm going to say something that's it was proved for linear logic, but it's more general. And from now on, there's only two ideas left, so I think I can present both of them. But both of them are now for classical semantics. So, as I mentioned, there was an initial expectation that we would be able to use the introduction rules of deduction to provide semantic clauses for the connectives. And that was shown not to be the case, but it is the case that you can, or at least it seems to be the case that you can always use the elimination rules to express the semantic clauses. So for instance, you can define implication this way, that A and B is valid if and only if from A follows B in arrays. Or you can say that A implies B is valid if and only if in every extension and for every atom, if you have a proof of A and you have that from B follows, that should be a C here, sorry. You have a proof of A and from B follows a proof of the atom C, then you already have a proof of C, which is the generalized elimination rule for implication. Okay, so and then those two are equivalent in intuitionistic logic. And you can also prove a similar equivalence in intuitionistic linear logic. I did not show the semantic laws for linear logic, but because you can see there's a lot more structure. But the proof of equivalence between the introduction version and the elimination version still works. And it turns out that we can even give elimination-shaped rules for the atomic support clause. So atomic support, atomic validity is defined in terms of derivability, but we could also define as in this way. So I have a proof of P if and only if in every extension and for every atom, if I can get a proof of that atom Q from the atom P, then I already have a proof of the atom Q. And it also works, as I mentioned, in intuitionistic linear logic. So this possibility of expressing everything in this shape seems to be a general feature of basic semantics. But okay, this is of course way heavier than this. So why should we do it in the first place? Because if we pick a semantics in which every clause is in elimination form, there is a very simple way of turning an intuitionistic semantics into a classical semantics. So, and this is really a very easy way. First, fix an atom Q such that the only special property of this atom is that it is a fixed atom. So we choose it beforehand, saying this is the atom Q that I will use in the semantic clause. If we fix the atom Q and we simply remove the quantification of atoms, then we immediately obtain a semantics from classical logic. And I will exemplify what I mean by that right now. So now we have these clauses in which you have quantification. So to say, for instance, let's look at this junction. You have a proof of A or B if and only if in every extension, and for every atom Q, if you get a proof of, if you can prove Q from A, then you can prove Q from B, then we already have a proof of Q. And we also have the same idea behind the remaining clauses. If we just erase the universal quantification, this is a classical semantics. It immediately becomes classical. Of course, Q is a fixed atom, but we just delete the universal quantification. And it's not clear why that is the case if we use an arbitrary atom key, but it is clear why that is the case when we use bottom as the notation. But I am saying that it's only a change of notation because we don't require any property of this atom bottom. It is a fixed atom and it's not, you don't require anything else. We don't require basically consistent. We don't require basically X false rules. It is just an arbitrary fixed atom. And I just presented it because it was easier to see for intuitionistic logic, but the same idea works in linear logic. So if you pick the intuitionistic linear logic semantics, both of the semantics, it works for both semantics, and we restrict the quantification, then it becomes a semantics for classical linear logic. And it is also interesting to notice that bottom is explosive in classical logic, but not in linear logic. So the idea works regardless of the explosive factor of bottom or not, and regardless of how much structure the clause contains. So it is a very general result. The paper that proves this on archives already, but if you prove it from classical linear logic, and okay, it is a very straightforward way of obtaining classical semantics, and it's interesting because this can be seen. I think that just like we can often obtain classical semantics by picking a cryptic model, like a crypt semantics for intuitionistic version of logic, and by restricting the models, we get classical semantics. We can also, by restricting the concept of proof, or what counts as a proof, obtain classical semantics in general. Okay, now the last idea that I'm going to present, I am quite glad that I got to present, in fact, all of the ideas, is ideas for bases that use sequent calculus. So natural reduction has single conclusions only. So it is a natural, it's very natural to consider in that setting intuitionistic logic, intuitionistic semantics. In fact, it was initially expected semantics completely was expected to hold because of the harmony of intuitionistic natural reduction rules. However, if we consider, instead of natural reduction, multiple succedent sequent calculus, it seems that the rules for classical logic are more harmonic than the rules for intuitionistic logic. So natural deduction is like a good fit for intuitionistic logic if you're thinking in terms of proof-theoretic harmony, and classical logic is better fit for multiple succedent sequent calculus proof-theoretically. So basic semantics itself is a better fit for intuitionistic logics because all the systems we have shown were initially intuitionistic and then we added classical structure later. But that might be only because we consider natural deduction in the basis. And in fact, we show in the result that for sequent basis that we can get an interesting classical semantics by taking, instead of sets of atomic bases that use reasoning in natural deduction, we take sequent calculus instead. And these are the semantic clauses that we use. Again, I will not waste too much time on the definitions. So let's just state here that we now use atomic bases which has sequent calculus rules, but there are a lot of features that has to be discussed, but for now it's just this. And what I would like to highlight in these definitions is that first, we now define validity for sets of formulas instead of just single formulas. And classical and atomic supports defined in terms of their validity. This holds if and only if I can derive the set atom, the sequence with the empty antecedent and the set of atoms gamma in the succedent. And the distinguishing feature of the semantics, I would say, is that we no longer need atomic quantification to define disjunction. We can, in fact, define disjunction to what would be its introduction rule in natural reduction. The same also holds for bottom. We now can get a definition of bottom which would correspond to what we would expect to see in the proof calculus, which is basically a definition of bottom in which you have a definition in terms of weakling. And again, we remove every reference to atomic quantification. There is a kind of atomic quantification here, because now you define validity for arbitrary sets. You also take into account arbitrary sets in the entailment notion, but I won't spend too much time on this. But the point is that these clauses are very harmonic, and it is a semantics for classical logic. And this is only possible if we add the extra structure that we use in the sequent basis. And as I mentioned, all semantic clauses are based on right introduction rules. If you look at the structure of the results, the presence of absence of atomic structural rules in basis, for instance, atomic cuts or atomic weakling, if you only consider bases close in the atomic cuts or bases that may lack atomic cuts, you get different semantic properties, but we have shown completeness both for bases which are cut-free, atomic bases which are cut-free, and atomic bases containing atomic cut. It is interesting to notice that if we use base close under atomic instances of cuts, we can straightforwardly adapt some disproof for intuitionistic logic. But if we instead consider cut-free bases, we have to be a little bit more creative. And this final remark is ongoing work. As I mentioned, we only consider the succedents of the sequence when defining support for atoms, but this is a semantics for classical logic. And the classical symmetry allows us to simplify and not need to consider this stuff at all. Also, there is no structural rules in the semantic, in the clauses, of course. And that is because of the symmetries of classical logic. But we might be able, and that's what we are working on, to refine the notion, but now consider, just like in the linear logics context, a notion in which we index a consequent relation by a set of atoms, and then we define that a set of atoms is supported, delta is supported in a base B by a set of atoms gamma, if and only if We can prove in the base there should be a derivability relation here. We can prove in the base B that from the set of atoms, the sequent gamma, sequent delta of atoms. And our expectation is that it will allow us to define also basic extension for substructural logics, but we have just started on this. So finally, just to recap the entire set of results. Finally, I am tired. So Bayesian semantics is useful in many different contexts, and it has, in fact, different semantic properties in many different contexts. In logical ecumenism, we can define different notions of proof, and we have shown it for classical intuitionistic logic. We can have an intuitive notion of constructive proof, intuitive notion of classical proof, and we can show that it yields the semantics for our logic combining them, which is quite nice. In bilateralism, we can, by introducing extra proof-theoretic structures in Bayes, show that some isomorphisms that are usually dealt with at the level of the calculus can also be given a reading in terms of the semantics and the isomorphisms in the bases themselves. I have also shown that we can get linear logic by including some notion of resource sensitivity, and there are at least two different ways of doing that. And both of them have very different properties and might be adequate for different contexts. We can also, if we have intuitionistic semantics, in general, obtain a classical semantics for the same logic by just restricting quantification, which is a very, very powerful and straightforward adaptation. And we can also, even though we can get these classical semantics in natural deduction by restriction, we can also get semantics specifically tailored to classical logic if instead of using natural deduction in the atomic basis, we now use sequent calculus for the basis. And perhaps we can even get in the future substructural logics in general. So that was it. Thank you.